Yeah, I'm ready.
Okay.
Good morning, professors. My name is Nguyen, and today I would love to present to you the results of my internship during these 2 months with Prof. Rafael and Prof. Etienne. It's about the modeling the dynamic of word retrieval process. So in my presentation, I would love to take you through the background and the method that I use in my study, and then I will discuss with you about the key results and the conclusion. So for many years, the scientists have long been curious about how the brain perceives and process the information. So they focus on the question, how can we see and name an object precisely? So to answer the question, they often use a mechanism that use the interference signal, which can be the auditory or visual or brain lesion, to manipulate the process, then observe the word retrieval process. So by measuring the reaction time and the error type of the answer, so scientists can infer the processing stages and their timing. So in prior study, they identified 4 typical stages in sequence. So thinking of an example of when we are looking at a piece of cheese, so the first stage of the word retrieval process is the conceptualization, when we build the concept about the object that we are seeing. For example, I see a yellow edible object made from milk. And then after this stage, we step into the semantic and lexical encoding stage, when we select the features explaining for the object that we see. For example, food, yellow, milky, smelly, and then the concept is more narrow and narrow down until you get the precise word, which is cheese. And then we step into the phonological encoding when we retrieve the phoneme sequence of cheese, for example, ch, e, s, and we rearrange them, order them to prepare for the last stage of the process, which is articulation, when our lips, our tongues, our larynx move together to produce the sound cheese. So, in the current view, the researchers mostly agree that the process likely lies on a continuum with a temporarily extended stage that can interact and allow in parallel processing for efficiency. However, researchers still disagree on the dynamic of the stages. So, when our brain perceives and processes the information of an object, not only the visual informations are processed, but also the psycholinguistic property of that object is processed. So psycholinguistic property are simply the characteristic of a word that affects how easily our brain can recognize, understand, retrieve, or produce that word. For example, if we look at the word if we look at the image of a cat and a piano right here, we see that the image of the piano have more details than the image of a cat. So basically, in this case, the image complexity of the cat is lower than the piano. Or when we're talking about the age of acquisition between the piano and the accordion, during our entire life, because we learned the word piano before the word accordion. So the age of acquisition of the word piano is lower than the word accordion. So image complexity or age of acquisition are the typical example of psycholinguistic properties. And researchers agree that these properties are processed at different stages, and you can see in the image here. And moreover, psycholinguistic property can be processed at multiple stages. For example, for the age of acquisition, it can be processed in both semantic-lexical encoding and phonological encoding stage. So in our study, we empirically divided a psycholinguistic property into 2 groups, which you can see on the screen. One group is about the conceptual psycholinguistic property, and one group is about lexical and phonological psycholinguistic properties. So back to the mechanism, when using the interference to understand about the dynamic of the process. So picture naming task is one of the tasks researchers often use to discover the semantic and lexical encoding. So in this task, there are two sessions. In the first session, the participants are required to name the picture presented randomly, and we call it the DS or baseline condition. And in the second section, with the same pictures, we send an auditory distractor at random time point, which we call the SOAs, to describe the semantic and lexical encoding. So the mechanism of the auditory distractor is, the more precisely we target the semantic or lexical encoding, the stronger interference effect can be, which can be presented as lower latency or semantic or lexical errors. But in our study, we only use the naming latency for the analysis. So in our study, we try to answer two questions. First, when does the interference begin to affect the word retrieval process? And second, how does it affect naming latency across the SOA condition, which is the session 2? To answer for this question, we also need to acknowledge a challenge. So remember in the session 2, because the participant used to see the picture once in the session 1. So basically, each picture is repeated once. So there's likely for the priming effect to appear and speed up the naming and masking the interference. So to measure the interference, we need to account for the priming effect. So to answer this question, we have to make two assumptions about the priming effect. First, the priming effect is constant across all the SOAs. So because each picture repeats once only in the session 2. And second, at 0 millisecond, as we remember, because the semantic and lexical encoding is the second stage of the whole process. So at image onset, it's too early for them to happen at that time point. So as SOA 0 millisecond, we assume that only priming effect. So we will use it as a reference to measure the interference, and I can show you in the later slides. Another limitation of previous studies is when trying to predict the naming latency, the researchers often used the regression model with a lot of psycholinguistic properties as the independent predictor for that. So that can cause some interpretation issue. So to address this issue, we also introduced in our study the principal component analysis method. It is a method that can help us reduce the dimensionality while preserving the information. So how does it work? So basically, in this method, the first step is we find a direction of seeing our data and can explain the maximum variance. And you can see here, the maximum variance is that when you projected every data on that direction, the level of spreading out is the maximum, is the highest. And second, if we find the BC2, which is another direction, orthogonal to BC1, and explaining the remaining variance, and so on. But in the analysis, we only retain the BCs that explain better than one single variable. So, from using the BCA, so from the 10 original variables that I showed you before, we reduced down to the 5 BC, as you can see on the screen. And this BC is contributed mostly by key loadings. For example, the BC Viscon 1 is contributed mostly by familiarity, image variability, or visual complexity. Or BC Lexicon 3 is contributed mostly by age of acquisition. So this BC will be used as the predictors in the linear mixed model, and we made 5 separate models corresponding to each condition: DS, SOA 0, SOA 150, 300, and 450 milliseconds. And then from the 5 models that we built, we extract all the coefficients of them, and we build a coefficient matrix. And we once again, we reapply the BCA, as you can see the illustration here. So on the BCA space, each point will represent one condition. And we compute the Euclidean distance between points. And it will represent what that larger distance equals the greater dissimilarity in model structure. So, from the method of our study, we have some key results. The first result is when we look at the SOA0 and the DS, we see that the SOA0 it displays from the DS. So, as we assumed before, this displacement is due to the priming effect. But when we compare the distance between, we compare the distance between DS and SOA0 versus DS and SOA 150, we see that this distance is larger. So in this case, because the SOA0 and SOA 150, they bear the same priming effect. So once push the model of SOA 150 farther away. So that is due to the priming, due to the interference effect. So from here, it suggests us that the interference effect begins to affect the retrieval process at 150 milliseconds. Second, when we take the SOA0 and the interference and we measure the distance to SOA 150, SOA 300, and SOA 450, we see that the distance increase and reach the peak as SOA 450. So it suggests that the interference is stronger when the distractor appears later. And we know the interference effect is getting stronger. But when we measure the distance between DS and SOA 300 and DS to SOA 450, we see that this distance decreases. So, it suggests us a condition when the priming effect pushes the model far away the baseline condition, when the interference effect pulls back the model near the baseline condition. So, in later SOAs, the priming effect is more counteracted by the interference, which make the models more similar to the DS. So, from this result of our studies, we have introduced a new geometric approach to the language research. So first, it helps us better understand the influence of the interference effect on naming latency in a picture naming task. And second, it helps us contribute more to the identification of the timing of the lexical and semantic encoding stage in word retrieval process. However, we need to acknowledge for some limitation in our research. First, the grouping of the psycholinguistic property into 2 principal components that I introduced before is mostly based on the prior observation. So, future studies should test the alternative grouping for the robustness. And second, the geometric analysis using the Euclidean distance that I introduced to you, what we can interpret the dissimilarity between models, but the statistical significance has not yet been established. So future validation of this method is also needed. So that's all for my presentation. Thank you for your attention and your listening.